what are the challenges in heat dissipation, and what are the what are the ways, what are the types of heat dissipations are there, and what are the impacts of thermal management. And then after this, we are going to see about the phase change. What is my thermal energy storage? And then PCM, phase change materials, and its properties of phase change materials. All those things only we are going to see. And finally, I'm going to give the applications of thermal management techniques in high power applications. That is the thing. So that I'm going to 1 or 2 slides. I want to show how this thermal management will be helpful to you. And finally, I'm going to discuss about the research activities at NIT Puducherry. So these are the main agenda of this presentation. We go. So first, let us see why heat dissipation is required. Nowadays, the semiconductor technology, a lot of advanced technologies is coming. So in this technology, if you see, more high power density components are involved in that. So high power density means more heat dissipations are there. So we need to eliminate that heat. Otherwise, that heat will be power losses will be converted into heat during its operation. What will happen if you not converting that heat? Means it will deteriorate the function of the devices. So it will malfunction will take place because of this, and because each and every equipment has some operating temperature. So if the equipment goes beyond this operating temperature, then it will be problem to us. So effective thermal management is a critical aspect in the power electronic system. Why we have to do this? We have to remove that excessive heat. That is the main thing. So why we are doing? We have to improve the performance of the system and reliability and lifespan. This is the main thing for the heat dissipations. If you see any components, any application, cell phone, self-driving car, smart TV, smart grid, aerospace, radar, camera, computer, and whatever the electronic components we have, definitely the integrated chips will be there. So in that integrated chips, enormous amount of heat dissipations will be there. So for that, in default, heat sinks will be there, that you know very well, heat sinks. And apart from what are the advanced technologies are there to dissipate the heat, all the things are there. So now here we are going to see about the types of dissipation, what are the its challenges, what are its challenges, how to dissipate the heat when you are trying to dissipate the heat, what are the challenges are there, and what are the advanced technologies are available. And with respect to thermal management of hyper application, what research work we are doing, that also I am going to emphasize here in this presentation. So we will see one by one. Anyhow, thermal management is must in the power electronic systems. So first, let us start with the types of heat dissipations. What are the types of heat dissipations? So normally, heat will be available in the electronic components in the power electronic systems. There are a lot of ways to dissipate the heat. One is passive cooling techniques. Other one is active cooling techniques, and advanced hybrid cooling techniques, and thermal behavior enhancement. So passive cooling means it is like heat sinks we are using. So without any external agency, without any external pumping power, we have to cool the system. That means fins. It is a technical term, means extended surfaces. That is called passive cooling. So fins already will be there, some extended surface. Like if you see dinosaur's body, some scales arrangement will be there. Why the scales are there? Because of this, to regulate the body temperature. Similarly, we are also going to attach some heat sinks, fins, to regulate the temperature of the system. That is without any heat, without any liquid flow, without any pumping power, without any electronic supply, without any electrical power supply, automatically it will cool. That is called passive cooling. Active cooling means we have to spend some energy to circulate the fluid. That is called active cooling techniques. A lot of cooling technique are there. We have to circulate the fluid, high heat transfer fluid, so that while pumping, while flowing, it will take the heat in and around the surroundings, and then it will come back. That is called active cooling. Advanced hybrid cooling, we will combine both passive and active and other techniques. That is immersion cooling. All those things are there. That is advanced. This is advanced hybrid cooling. The last one is thermal behavior enhancement. Thermal behavior means we have the system. We have to analyze the system based on the system's heat sources. We have to provide the path to eliminate the heat. This is the based on the system behavior, that is thermal behavior, and then we have to enhance the heat sinks arrangement, all those things. These are the types of heat dissipations are there. Let us see one by one what are the techniques are there also elaborately. Now, first one is passive cooling. I already told you passive cooling means it is like a natural, naturally it will transfer the heat. So here we will not circulate any fluid, any pumping power, any extra power will not be supplied here. It will be taking the heat naturally. That is called natural convection and conduction and radiation. That is natural convection and conduction. Conduction means you know very well, solid to solid. Convection means solid to fluid. Fluid means air or liquid, other thing. Radiation means by means of electromagnetic waves, it will transfer the heat. This is the passive cooling. In that, mainly they will adapt heat sinks. Heat sinks means some projected object will be there wherever the heat sources is there. That projected object, that's why already I gave one example. Everyone will seen the dinosaur's body. In the dinosaurs, a lot of scales are there in the body. The scales are why it is there means to regulate its body temperature. So similarly, we are also going to use the wherever the heat sources is there, in that below that heat sinks will be there. That is my means of passive cooling. We are not circulating anything. Naturally, it will cool the things. So now how to optimize that is in that lot of to enhance the thermal performance of the heat sinks, we have to study about the surface area optimization, how many number of heat sinks, how many number of spacing between the one heat sinks to other heat sinks, all those things we have to study. This is the passive cooling. Other technique in the passive cooling is thermal interface materials. Thermal interface material means some material will be some low resistance material will be provided to improve the heat transfer. So that normally what will happen, the resistance will be more. That's why heat transfer is not effective. That resistance we have to we have to remove that barrier, so that thermal interface materials will be TIM will be introduced, so that to reduce the thermal resistance between the heat source and to transfer that to the medium, so that it will effectively transfer the heat, so that the heat transfer efficiency will be more. That is the passive cooling. One of the thing is passive cooling. The second thing is active cooling techniques. Active cooling means, if you see here, forced air cooling and liquid cooling systems are there. That is forced air cooling means here we have to spend some energy. Then energy I'm telling means spend some power. Say for example in the CPV, CPU is there. That is in the computer CPU, backside you can see the fan. For that fan, where it will take the power, it will take the power from the system itself. So like that, some additional power is required to operate this. That's why it's called forced air cooling. That is, air is forced. Forced means it will be admitted by means of fans or blower to remove that heat effectively. So why we are doing all these things means, suppose if you have hot coffee in your hand, hot coffee, if you keep that hot coffee in the room or thing, automatically it will cool, because ambient temperature is very cold when compared to the hot coffee. So it will slowly it will reduce the heat. Slowly the hot coffee will become cold coffee. Okay, it will be getting that heat will be evolved. Same thing, if the same hot coffee, if you keep it under a fan, what will happen? Very fast manner it will cool it. So it will remove the heat. So similar kind of thing, forced air cooling. So it will be enhance the heat transfer coefficient. That technical term is called heat transfer coefficient. So that is the coefficient. That heat transfer coefficient means that is the how much amount of resistance is there, that will be overcome that resistance. The whatever the forced air is there, that will overcome the resistance, so that effective better heat transfer will be there. This is the forced air cooling. The next is the liquid cooling system. Liquid cooling system means some channels will be there, some pipes will be there. So in that we have to circulate the coolant. What is the property of the coolant? The coolant while going it will takes the heat. While coming it will deliver the heat to the other places. So that is called liquid cooling system. These are all because for circulating the coolant we have to pump the fluid. For that, from motor or some pump will be there. So for pump will be operated by the electric motor something. So that means electrical energy you have to spend. That's why it's called active cooling techniques. So in the active cooling technique is better heat transfer when compared to the passive cooling. So is the passive cooling is the heat sinks we are seeing, and the TIM, and the active cooling we are seeing forced air cooling and liquid cooling. So active cooling we have to spend some energy actually. That is the thing. But the effective heat transfer will be there. And the next is the advanced hybrid cooling technique, that is two-phase cooling systems. and micro channel and jet impinging cooling and immersion cooling. These are the coming under the advanced cooling methods. So here the two phase involved. That means while admitting the fluid, it will become liquid. After capturing the heat from the power electronics system, where high density, where high heat is there, that liquid will be converted into vapor. So that's called heat pipes. So the heat, these are all very effective two phase. When you term two phase means it is better than the forced convection. So whenever the phase change occurs, phase change means two phase flow. That means phase change, effective heat transfer will be there. More amount of heat, that whatever the term I said, heat transfer coefficient, that will be very, very high. That is the thing. These are all for effective heat transport, these things. And the second one is called micro channel and jet impingement cooling. In the micro channel and jet impingement cooling, in a very small compact area, where you are accommodating all these systems, in a very small area, we have to send the fluid. Actually, here also fluid will be circulated, but only thing, small quantity of fluid, but very effective. But only thing challenging is very compact. It is very compact actually. Very small area will be there. So in micro channel means, you see micro channel. The channel is micro channel. It is in micro size. In that we have to admit the force to the fluid. We have to admit the fluid to flow through this micro channel, so that it will takes the heat. It will take the more amount of heat from the heat sources, and then it will deliver it to the other places. So maximum amount of heat transfer will be taking place. That is the thing. Immersion cooling means, so here that is whichever you want to transfer the heat, the devices are completely submerged in a thermally conductive dielectric fluids, so that uniform cooling will be there and superior heat dissipation for hyper application. This is another type of cooling. These three conditions are advanced type, advanced hybrid. So the immersion coolings are in a conductive dielectric fluids, and uniform cooling will be taking place. Whatever the heat transfer coefficient I said, in the passive cooling, it is value will be very less. Say for example 0 to 10, passive cooling means watt per meter square Kelvin. That means 10 means very low. Like hot coffee is you are keeping in the ambient condition. Now the same hot coffee, if it is in the forced under the fan, that is heat transfer coefficient is very high. So you can say the magnitude around 25 to 50 watt per meter square Kelvin. Now the same thing, you are coming to the two phase flow and the micro channel and immersion coil. The heat transfer coefficient is very high now. Now you can imagine that is, instead of 50 to 100, it will be in terms of 1000, 500 to 1000, like that. So the heat transfer coefficient is very, very high. So that heat transfer coefficient is very high means what will happen? The thermal resistance are getting low, so that heat transfer is effectively, that parasitic heats are removed from the systems. That is the thing. And the last one is thermal behavior enhancement. So whatever the heat sources, because heat sources are not, if you see integrated, that is circuits board, here one chip will be there, other one chip will be there. The heat sources are not in the randomly, it will be distributed. So accordingly we have to simulate that environment, and then we have to, that is simulation means computational fluid dynamics model you have to create, and then effective cooling design you have to create. Optimized manner you have to create the thermal behavior. We have to control the thermal behavior. That is called thermal behavior enhancement. These are some of the heat dissipation techniques are available. That is thermal behavior enhancement. So these systems, why this system, most of our electronic cooling devices, the main thing is this CFD they will use. That is mainly ANSYS software they will use. ANSYS software. In that they will model the entire heat sources, and then they will sometimes they will circulate the air, or the air is passed through, or some fluid is passed through, how the behavior will be there. They will calculate the heat transfer coefficient. That is heat transfer coefficient in terms of Nusselt number, they will say. If it is that Nusselt number is one of the non-dimensional number, Nusselt number, how it is effectively remove the heat. The more the Nusselt number is, more convection will be there. Less Nusselt number means that is convection is very less. That is the thing, magnitude. So like that, it will, thermal behavior enhancement is taking place. That is the thing. So these are the different types of heat dissipations are available. Now, when you are dissipating these heat types, what are the challenges involved? That we will see that. What are the challenges involved in that heat dissipations? So whatever I said, passive, active, and then advanced cooling technique, that is micro channels and jet impingement, and then thermal behavior, immersion coil type, all those things. When you implement all these things in the electronics, power electronics, what are the challenges you are going to face? That is the thing. So here, if you want to effectively manage that is thermal management of heat in power electronic systems, these are the problems, challenges are there. Okay, so we will see that what are the challenges task. High power density and miniaturization and material and interface limitation, dynamic and non-uniform thermal loads, reliability under harsh conditions, integration with advanced systems, optimization of heat sink designs, cost and performance trade-offs. These are the seven challenging tasks are available for the heat dissipations. We will let us see one by one what are the things. So high power density and miniatures. Here, what is happening? No, whenever you want to dissipate the heat, that is normally increased power density will be there. Power density will be there. So that the power density is increased means normally high heat generation will be there. And which is, but the only thing is this high power density in high heat generation is taking place in a smaller volume. So what is happening? Our task is to remove that heat effectively from the smaller volume. So we have to difficulty in the heat dissipation without the compromise reliable. This is one of the challenging task in that. And then small volume, I said, that means smaller surface area will be available. So the surface area is available means, heat transfer means Q is equal to HA delta T. You know very well, Q is equal to HA delta T. Q is the heat transfer and H is the heat transfer coefficient, and the area is the area, surface area, and delta T is the temperature difference between that. Here Q is directly proportional to area. If the area is very small means what will happen? Heat transfer is also very small. Quantity of the heat transfer removal rate is also very small. So this is the thing because of miniature in the power electronics and high power density. Both the things are involved. It is small size, but a high power density. All these things are one of the challenges of the heat dissipation. So this here, that's why this advanced cooling technology, you have to think about that. This is one of the way of one of the challenging tasks we are getting while implementing the things. And the second thing is material and interface limitations. Material and interface limitation, if you see, normally if you see here, traditional material, because I hope you know that what is thermal conductivity. When you transfer the heat, this thermal conductivity play a major role. Material thermal, because copper is having thermal conductivity of, the copper value is around 386. Okay, the aluminum, if you take aluminum, it is around, copper is value around 400. Aluminum, if you take around 200, 210 something. So this value, if you take steel and all, 50. So like that, thermal conductivity play major. More high thermal conductivity, very effectively to transfer the heat. So we cannot, when you install this, material limitation is also there. That is the thing. What type of material we have to insert, what type of things, because you cannot insert the huge weight, high thermal conductivity. What will happen? Weight will be increased also. That is also there. So this traditional materials, you have to, in the modern system, you have to meet the thermal demand. It is also some struggle is there, some problem is there. Apart from that, when you want to reduce the thermal resistance in the interfaces like heat sinks and thermal interface materials, this effective, this K value also we have to check. That is thermal conductivity of this material. That is one of the bottleneck of the efficient heat transfer. This lies in the thing. This is another challenges of the heat dissipation, materials and interface limitations. So we cannot keep on the insert the material, but weight also will be more, and then material capability also. What is the heat transfer capacity of the material? What is the K value? How efficiently it will transfer the heat? That is also there. And the third challenges is dynamic and non-uniform thermal load. So what will happen? The heat sources are here and there will be there, and it's not uniform thermal load across the device. So in one place high density will be there, where high heat generation will be there. In other place low heat low density will be there, low heat generation will be there. Similarly, other places high density will be there, high generation will be there. So here some thermal hotspots are there. It is non-uniform thermal loads. So accordingly, you cannot consistently, you cannot keep these materials throughout the system. So we have to, some restrictions will be there. So non-uniform thermal model, and also it is a dynamic. dynamic very fast changes. Something will be in some of the conditions, high temperatures and dynamic operating conditions. In dynamic operating condition means some of the systems will be operated at high temperature and some of the systems will be operated at low temperature. We cannot implement the same material for both the conditions. So like that, why I'm telling temperature play a major role means the temperature also affect the variation of the thermal conductivity with respect to temperature is also there. That is also play a major role. So as the temperature increases, K value also decreases, material of K value. So that's why dynamic and non-uniform thermal load is also there. That is the thing we have to take place. And then reliability under harsh conditions. That means reliability under harsh condition means defaultly the power electronics involved in the industrial and automotive applications where the harsh environmental conditions such as high temperature, vibrations and humidity, all those things are also undergone. There also we have to environmental condition also we have to see. We have to see that high temperatures and vibration, all those things. These conditions definitely these conditions will degrade the thermal management materials. So vibrations, some high humidity, high temperatures, because high temperature, why I'm telling means you are inserting the material at high temperature means, so the whatever the K value is supposed to dissipate the heat, when the temperature increases, the K value will be reduced of the material, so that your heat transfer also will be reduced. That is the thing. So hence the thermal management will degrade according to the environmental conditions. So that's the reliability of the power electronic system also will be questionable actually. How long it will come, all those things. So these are some of the challenges are there in that. I hope I am audible now to you. Hello.
Yes, sir. You're audible, sir.
Yes, sir. Thank you, sir. Thank you. Next is the integration with advanced system. Sometimes we have to integrate the power electronic system, some advanced system. Say, for example, electric vehicles and renewable energy converters. All those, because if you see electrical vehicles, sometimes we cannot increase the load, we cannot increase the weight. So that if you increase the weight, what will happen? More amount of force is required to run the vehicle. That is also there. So when you integrate these power electronic systems in advanced system, there is some limitation is there with respect to materials, all those things. So lightweight should be used, and in that lightweight, highly efficient also should be there, and then scalable cooling solutions. All those things are some of the challenging tasks are there. So are dissipating the heat. I hope you understood, because in the compactness of the vehicle, more weight. If nowadays if we see cars, light vehicle, yes, light vehicle means more mileage will be there. That is the thing. So what will happen when you integrating this power electronics with advanced systems? We have to take care of these materials also, that lightweight component, highly efficient, all those things. This is another task, another challenging task involved in the heat dissipations. And the last thing is the optimization of heat sink designs. Optimization means so where you have to design the heat sinks properly. That is numerically we have to do some simulation, and then we have to balance the thermal performance, cost, size, everything. Such things, even for portable devices, compactness also, we have to increase the, that is, we have to design the heat sinks. Numerically, we have to design, and then we have to check in the things. Experimentally, we can do that. So that optimization is very, very important, where you have to place the heat sinks, where you have to place how many number of fins, all those things. This and all, you have to do the simulations, and then only you have to put it. You cannot just like that. You have to design it properly. You can design number of for this area. This much area is there in that area. This much fins, number of fins you can design. But how optimize it? You have to orient the fins and what position it have to turn. What is the orientation of these things? All those things are very, very challenging task that we have to overcome it. Actually, that is the thing. And the last challenges is cost versus performance. Cost versus performance means we have to think about the that is cost. Whatever you cannot increase the cost also at the same time, because normally electronic components are cost very less actually when compared to the mechanical or civil components. So this electronic components, if cost, if you want more means, then it will be also thermal management cost. Also we have to see the trade-off cost between the thermal management performance and the performance and the cost. All those things. Sometimes high performance cooling such as liquid or immersion coils are often expensive, but high heat transfer coefficient we are getting in that only. But at the same time, you have to recommend for Anyhow, the power electronics entire system cost is around 1,000 rupees means accordingly only you have to propose the cooling system also. If the power electronic cost is around 1 lakh means accordingly only you have to propose this. So you cannot propose for 1,000 rupees electronics, you cannot propose 10,000 rupees cost. So some cost trade we have to optimally you have to do that. The trade-off you have to do the based on the performance and the cost. So these are some of the challenges involved in that. And what are the advanced cooling technologies in the power electronics that we will see that I will show in terms of picture also some of the things we'll see. Now the advanced cooling technology means anyhow why all these things we are doing means to enable the to
Sir, hello, Sendhil sir. Sir, Sendhil sir, are you? Am I audible, sir? Hello, sir. Sendhil sir, am I audible, sir? Participant, kindly wait. We are waiting for the chief guest to join once again. I think there is some network issue from his side. We are awaiting for his presence. Sir, now you have joined, sir. You may present now, sir. Sir, your screen is visible, sir. You may present, sir. Sir, I think your voice is not audible, sir. Can you unmute yourself and present, sir? Please, sir.
Sir, now is it audible, sir?
Yes, sir. Now it is audible, sir. Clearly audible, sir. Now you may present.
Yeah, thank you. So next, we are going to see about the advanced cooling technology in the power electronics. So advanced cooling means what are the different technologies also we can use. Now techniques like thermoelectric cooling and high temperature phase change materials. So this will enhance the thermal performance of the that is enhance thermal performance of the, even though small compact system is there, that you can use it here. Thermoelectric cooling and high temperature phase change materials, so that it will enhance the thermal performance of the power electronics, so that effectively heat transfer will be taking place. So that is the thing. This one is a thermoelectric cooling. That means based on the Seebeck effect. That is, once the delta T is wherever the high temperature is there, there you have to keep this thermoelectric cooling so that it will cool the things. So other side we will produce the cooling also, and other in the we have to supply the thermoelectric cooling. There is a difference is there. Thermoelectric generator and thermoelectric cooling. Thermoelectric cooling means we have to use the power supply here. In that power supply, that is Peltier effect. Here it will, one side it will cool it, other side will be we are giving the heat also, so that this cooling means the cooling side will be placed in the power electronic side, so that your power electronics devices will be cooled. And other one is phase change materials. Phase change materials, high temperature phase change material means so phase change means at normal temperature will be in the one phase. When the temperature increases, the phase will be converted. That say for example, liquid will be converted into vapor. So that is the phase change. So now the vapor phase, it will absorb all the heat, and then when it coming, and then it will deliver the heat. It will transfer the heat to the other fluid, and then again it will become the vapor to liquid, and again liquid will be circulated back to the devices. Like that, circulation will be that is called phase change materials, PCM, phase change material. That is the another that is the high temperature environments. These are some of the cooling optimized cooling strategies. And then this thermal performance in high performance packages. So whatever we discussed, thermal interface materials, so that we have to use it with high thermal conductivity. Anyhow, high thermal conductivity material we have to insert it, so that this high thermal conductivity means low resistance will be there between the layers. So these things we have to take care into this account while transferring the heat. So that is thermal interface materials with high thermal conductivity. That is the thing. So that even though if it is in compact devices, area is very small, surface area, that you have to take care of. And then micro channel cooling. This is another things, advanced cooling, micro channel. Here the micro channel, if you see here, if we see here, micro channel means the channel is in a micro type, actually small type. In that you have to insert the, you have to penetrate, you have to, that is admit the fluid to flow through this micro channel, so that it will take the heat. Whatever the heat is available in the power electronics system, it will take the heat, and then while coming back, it will be taking the heat, and then it will dissipate to the other places. So this is the highly efficient, because whatever I am telling here, this heat transfer coefficient, I think those who are working in this area, they know that heat transfer coefficient, that H should be very high. Then only your heat transfer coefficient very high means then only you are effectively removing the heat transfer. So where if you want to, because this and all cost involved actually, micro channel and all, because we have to circulate the fluid. For that circulating, some pump you have to operate it, small pump or small thing. For the pump means motor will be there, motor it should be powered. So sometimes where will be precise thermal management in a confined spaces, there the micro channel cooling you can enable it. You can use it actually. That is the things. And another thing is hybrid coolings. This hybrid cooling. So here sometimes heat pipes. I hope you know the heat pipes and vapor chambers with liquid. That is, you can also combine active and passive cooling technique. Whatever we discussed about the things, active and passive cooling, along with that is heat sinks, along with the heat pipes. You can integrate this in a system, so that the thermal load will be removed. Whatever the transient thermal load, whether in the steady state or transient thermal load, in a dynamic chamber, in a dynamic state it is there, means there you can use it to overcome this problem. There hybrid cooling technology, that is integrating the heat pipes, heat sinks, that is active and passive cooling technique, you can integrate it, both it combines. And another thing is the emerging dielectric cooling techniques. That means whatever the system is there, that you have to impinge it. You have to in a immersion cooling, that is advanced dielectric liquids such as like mineral oil, castor oil, all those things. They will provide the cooling platform for that hotspots. Cooling platform means what will happen? It is like if suppose if hot coffee is there, what will happen? Sometimes they will you can immerse in a water and then they will remove the heat. No, same manner only. So that if immersion cooling techniques also should be there. Wherever the hotspot is occurred, there we have to immersion, that is dielectric cooling technique. You have to adapt it to remove the hotspots. And if you see all these things, this advanced cooling and all, if you see the parameter, that is natural convection, forced convection, liquid cooling, micro channel cooling, and immersion cooling. If you see efficiency wise, micro cooling, that is immersion cooling techniques, almost you will achieve heat dissipated 95 to 97%. You can achieve it, heat transfer coefficient, because heat transfer coefficient is very high. Immersion cooling means suddenly you are increasing, suddenly you are exposing that environment in a cooling fluid. So what will happen? So cooling heat transfer coefficient is very high. That's why heat dissipation is also very good. That's the efficiency is also very good. And other thing is heat dissipation. Heat dissipation will be 100%. You can say that 100% heat dissipation you can say. Whereas the natural convection, if you see, are only 14%, because natural means through natural conduction, radiation only, this will be dissipating the heat. So it whatever there's some limitation will be there because of thermal resistance will be more. Heat transfer coefficient is also very less. That's why efficiency is also very less, 30%. And the temperature increase. Temperature increase means what is the rise in temperature? Rise in temperature in immersion cooling, you can see almost 16% only increase in that. Whereas in natural convection, 90%. That's why this efficiency is also very less. In heat sink, natural convection means it's coming under the heat sinks. Heat sinks means properly you have to do the simulation, you have to see the behavior, and then you have to optimize the things, and then you have to eliminate the heat. If you see the immersion coil, immersion cooling type, almost 16% temperature increase only. So whatever the surface temperature is there, only 16% rise in temperature will be there. So that is the temperature rise means delta T. Whatever the delta T is there, that we are minimizing. That is the thing, immersion cooling. And then that what is the reliability of that electronic components? Reliability will be that is reliability lifetime is it depends on temperature. Even 50 degree, you can see at 50 degree 100% reliability is there. Whereas the environment goes beyond this 50 degree, whether this natural convection will not work. If you see the immersion cooling here at 150 degree, 20%, that is the reliability lifetime. So that is the reliability will be increasing actually. Even that worst condition also, even so it will work at 50, 100 degree, automatically will work. Reliability will be 100%. Only at high temperature only you have to think about that. So that reliability of the lifetime will be at, it will vary from temperature to temperature. That is in which low temperature, high temperature, medium temperature lifetime will be there. So at high temperature means the reliability case also will be there. So that immersion cooling techniques in a small area, it will be good actually. And forced convection and liquid cooling and micro if you see, the efficiency is around 60%, whereas liquid cooling around 85% heat dissipated, and micro is 95%. But these are all cost involved also, because whenever I said that is natural convection means there is no need to spend energy. Forced convection, liquid cooling, micro channel, immersion cooling, we have to spend some energy. That is the thing. Energy means power. That is the things. So this is about the advanced cooling technologies in the power electronics. What are the things are there? So if you see here, the same thing. Here, if you see micro channel cooling, what are the impacts? If you are adapting the thermal management system, means what will happen? Your system reliability improvement will be there. So reliability 10% chances are getting. That is 10% only improvement will be there. Here 58% improvement will be there. Whatever the expected time duration will be there. Say for example, lifespan of the increase thing will be increased, and thermal stress reduction, because thermal stress reduction is very, 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 very important. That is the first priority of the thermal management. That reduction will be occur in the micro channel, hybrid cooling, liquid cooling, all those things. In the natural condition, the thermal stress will be there when you are operating the power electronics. That is around 20% only. The heat removed efficiency in natural condition very less, whereas the micro channel, liquid cooling and all very high. And then the thermal resistance will be very high. Very high means because there we are not inserting any barriers. We have to integrate with the thermoelectric cooling or in some high thermal conductivity, thermal interface material we have to, then only the thermal resistance will be increased. The thermal resistance will be reduced. Then only heat transfer will be more. The temperature reductions, almost 85% temperature reductions will be there in the cooling technologies. So system efficiency will depends on temperature, at what temperature it's operating at. That is very important. So at 95% micro channel cooling efficiencies will be very high, whereas the natural convection means it is 30% only. So at 150 degree, still if you 50% it is okay, but when the temperatures increases, the natural convection will not play a major role, and forced convection only in the high cooling technologies, micro channel or hybrid cooling or immersion cooling only you have to prefer it. These are some of the harsh environment goals. To the normal environment, natural convection system is okay, but at the same time, operating temperature also you have to maintain it. That is the thing. So these are all about the impact of thermal management. Now I hope you know what are the ways to dissipate the heat, what are the ways to dissipate, what are the challenges involved in that, and what are the advanced cooling technologies is there. In that advanced cooling technology, I mentioned that thermoelectric cooling and high temperature phase change materials. In some of the research papers, seen phase change materials they are using. PCM, they used to say PCM. So I will give some introduction about the PCM so that you will come to know about the what is PCM, how to select the PCMs, all those things. So that some useful information you will get about the PCMs, that we will see that. So accordingly, you will have some idea about the what type of PCM you have to choose, all those things. So here the thermal energy storage means, so whatever here we are using for our application, we want to store the energy. That is the thing. So your application, that is in the power electronics, I mean, we have to dissipate the heat. We have to take that heat, or it will store the heat, and then whenever the phase change occurs, it will release the heat. So that means at one phase it will take the heat, and other phase it will release the heat. That is the thing. So here a lot of applications are there, that is thermal energy storage application. So let us see that why the thermal energy storage. What is thermal energy? Thermal energy storage means sensible heat and latent heat is there. So sensible heat means it will not undergo any phase changes like our sand, concrete, all those things. It will undergo, but that we are not interested in that. We are interested only in the latent heat storage. So during the phase change, how much amount of heat storage it is there? That is the thing. So that is the ice and water is there. When it is a water, how much amount of heat can be stored? When it is at ice, how much amount of heat is stored? When it's ice became a water, heat will be released. That's why the ice became the water, all those things. So this is the latent heat, phase change. During the phase change, how much amount of heat is absorbed? And apart from thermochemical storage is also, there is different types of energy storage. That is metal oxide, that is not applications that we will see that. So sensible heat, latent heat, and thermal chemical storage is there. If you say thermal energy storage, this thermal energy storage, I will go a little bit faster. This is so thermal energy storage means one time it will be charging and other time it will be discharged in a short duration of time. That is the thing. So say let us take a solid phase change material. During its melting, because whenever the heat is there, it will absorb the heat so that the solid will become liquid. And the liquid, whenever it transfers the heat to the other film, and the liquid will become solid, that time it will release the heat. That's called phase change process. So this phase change or latent heat storage, both are same. Phase change material or latent heat storage material, it is more efficient to store the heat and then you will release the heat. That is the thing. So how much energy per unit mass, that is very, very important in the phase change materials. During freezing, how much it is, during releasing the heat, how much heat is transferred, that is very important here. So here the state will change, solid to liquid during melting, and again during solidation, the liquid to solid. It will be there. This is the phase change. So here, if you see, this is the curve temperature. As the temperature increases, the phase changes. Solid to liquid will be there. Up to this, will liquid. You can see here, and then leaking liquid to vapor. So this is the how much amount of heat is absorbed. Latent heat of fusion and latent heat of vaporization. How much heat is required to convert the solid to liquid? This is taking place at a constant temperature. That's why it is flat. Okay. So during the energy, during the heat, whenever the high heat is available, so if you place that phase change material, what will happen? It will take the heat. It will become phase changes will take place once, and then we have to give the space for to transfer the heat also, so that automatically the heat will be transferred to the ambient. That is automatically once it is heat will transfer, it will become to the normal state. That is a phase change. So you can see solid to liquid, liquid to vapor, like that. This is the phase change process. So this is the another sensible here. Only during because melting point will be there. Say for example, wax. If you take wax once it is at melting temperature is around 58 to 60 degree is the melting temperature. Once it is increased beyond that, automatically it will melt. So during melting, it will absorb some energy. It will absorb here. It absorbs some heat. Actually, what will happen? It will become completely becomes liquid. Once solid wax will become liquid, and then after that, what will happen? It will transfer the heat. Slowly, it will transfer the heat. After that, the liquid wax will become again solid. It is a phase change. That is the thing. So these are different types of phase changes. Is there solid to solid, solid liquid, solid gas, liquid gas? All those things are there. In that organic PCM is there, inorganic PCM is there, eukaryotic PCM is there. In that organic, we have paraffin, non-paraffin is there. In that inorganic salt, most of the salts are coming under the inorganic. For high temperature, we'll use inorganic. Eukaryotic means it's a mixture only. Organic, inorganic, organic, like that will be there. So normally for low temperature application, organic PCM. Normally for high temperature, inorganic will be there. So organic will be around 50 degree, around like that. So if you see here this slide, you will come to know solid means rock, mineral, metal, sensible heat. Liquid, latent heat storage means you can see here liquid to gas, solid to liquid, solid gas. If you see given alcohol, paraffins, esters, inorganic means salt, metal alloy, metal compound. All those things are depends. That's why we are using the some of the sensible heat means in the heat sinks. It's not melting. It only transfers the heat. That is coming into sensible heat storage. Whereas in the phase change material means it will melt and then it will transfer the heat. That is the thing. Sometimes chemical reactions also will be there. Chemicals will be solid to liquid. Some polymers will be there. So there also some heat storage will be there, and then we can remove it also. That is the thing. So this is the how much amount heat is required per liter melting point. What is the melting temperature of that? It depends on your application. You have to choose fluorides, carbohydrates, chlorides, hydroxide, nitrates, sugar, alcohol. If you see that, the temperature will be minimized. Gas, fatty acids, water, all those things. And it depends on your application. You have to choose. You have to check the properties of the PCM. That is another thing. You can see here organic PCMs that is available. You have to see the cost also very important. I said already, cost and the performance trade-off. So this organic PCM like paraffin, non-paraffins are there. But the main thing is paraffin's melting point temperature is 35 to 70 degree. You have to choose your paraffin, that is organic PCMs, according to your application. Non-paraffin means it will be mainly for thermal comfort application, low melting point will be there. So accordingly, you have to choose the, here I listed some of the organic PCMs, octodectane, tricosane, tetracosane, oleic acid, capric acid. Some of the organic PCMs are there. Their melting point is also the 29 degree, 41 degree centigrade, 48 and 69 degree, 51 degree. So like that, these organics are low temperature. But only thing is latent heat storage. You see how much amount of energy can be stored. 244 kilojoule per kg. That means per kg if you store this much 244 kilojoule of heat only it will be stored. So similarly, what amount of heat capacity it will be stored? What is the specific heat? How much amount of heat is required? What is the K value, thermal conductivity, what is the density, all those things you have to, anyhow, you are on the electronic side, but at least when you are choosing the material, you have to see the thermophysical properties of this. And this is about the organic PCM. The main drawback of the organic PCM is low thermal conductivity. There most of the organic PCMs are coming under 0.2 watt per meter Kelvin. Sometimes we are adding some other composites, some graphene, some high carbon, so that to enhance the thermal conductivity. That work also we are doing. Actually, maybe you can also try with PCMs with different composites, so that the K value will be more, your performance also will be high. Some inorganics means some salt only. It depends on the temperature, what range, when it is operating at very harsh environment, high temperatures. So melting temperature will be depends on melting point you have to choose on 10 degree, 100 degree, or 90 and 200 degree, 300 degree, like that. So these are this mainly inorganic salt will be used for our solar application. For solar things, we are using this. Immediate cooling, if you want, you can use that. That is the thing. That is this is one of the thing is this in the thermal aspect. You have to see that When you have to see how it is corrosion effect also you have to see. It should not corrode the power components also. That is also very important, whether it's chemically stable or not, whether high cooling effect is there or not. That is one of the limitation. You have to check it actually. These are some of the inorganic compound and their melting point, and then latent heat values also are given. If some of the things are around 8 and 900 degree, it will be operating at high temperature. We are operating that high power applications. You can think about the salt also, inorganic PCMs. So that this will be some of the useful information you will get where you can use inorganic PCMs for your application, all those things. Here, the latent heat also you have to think about that, how much amount of heat will be stored. That is also there. And metal alloys, PCM. Here, inorganic types, here K value will be very high. Only thing is, latent heat will be storage is very less. That is another drawback here. Whereas in the PCMs, in the organic PCM, the K value is very less and the storing capacity will be very high. High means it is okay, but here it is a low latent heat storage. That is all there. That we have to think about that which component we have to add, which composite. That is the things. And this is the I just want to show the picture phase change materials in the original paraffin wax, stearic acid, and sodium hydroxide. All those you can think about in your electronic sites. These are some of the desirable thermal property. What are the properties is required? It should be suitable melting point for particular application, and then high latent heat, high thermal conductivity when solid and liquid phases, and high specific heat should be there. And similarly, physical properties, high density and small volume changes should be there. If suppose volume change is very high, means your entire power system will be occupied. That is so volume change also will be very small, and low vapor pressure to reduce the contaminated problem, all those things. That these are some of the properties, desired properties of the PCM. And the chemical properties. Chemical properties means here no degradation, because more number of cycles, because you are going to operate via switch on, switch off. In the electronic components we are going to do, number of cycles will be very high, number of cycles will be very more, and it will undergo the number of heating and cooling, like that will be there. So that whenever different heating and cooling cycles are there, how much degradation will be there, that also you have to check it. That is very, 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 very important things in the PCM. Stability, whether after suppose n number of times you switch it off, switch it on, it is again it undergoing the heating, cooling, there is no use, means the property degradation will be take place. That is very important. You have to check here, organic PCM or inorganic PCM. What is the thermal cycle analysis separating? What is the corrosiveness? It should be non-corrosiveness of the construction material. Chemical decomposition should not be there, and the toxicity will be less. Non-flammable. When you are operating this, whenever heating is there, flammable gas should not come. So that's a non-poisonous, non-flammable. All those things you have to check this. And another economic criteria, cost also very important. It should be easily available, and it should be low cost, available in plenty. All those things you have to see. And all these criteria you have to take into consideration, and then only you have to choose the PCM, phase change material selections. Otherwise, your application will be wasted. So whatever the application, it depends on your application only. You have to choose, and then you have to make this. No, and another one more thing I'll tell you: no single PCM will be satisfy all your requirement. You have to mix it, or you have to combine it with other composites, and then only you have to do that. But well and good, if it is applicable to your application, then it is okay. So low thermal conductivity, I already told you, low thermal conductivity of PCM and the variation in thermophysical properties of PCM on different sectional cycles. Cycles means heating and cooling, and phase segregation, subcooling. These are some of the drawbacks of the phase change material. That is volume change and high cost. All those things are the lead to the restrict the efficient performance of the PCMs. So these values and all you have to check. We have to see how to add, how to enhance the K value. How to enhance means normally PCMs are there. I want to add another material so that your PCMs will be enhance the K value. So your PCMs will because normally K value will be very low. After adding the material, the K value will be enhanced. So like that you have to check it actually. It only depends on, purely depends on the what application you are going to keep it. Normally for your applications, heat transfer application, K value is very high, means it will be good. Actually, normally all the PCMs are K values are very less. Anyhow, you have to think about the composite to add in that phase change. So So if you see here, one of the two properties, that is thermal conductivity and thermal stability. So if you see here, for organic PCM, 0.15 to 0.3 watt per meter Kelvin, that is the K value. But if you see the thermal stability, it will come only the 3000 cycles, 900 cycles, 1000 cycles, 1500 cycles. After that, what will happen? Its property will deteriorate. We have to, before putting into the application, we have to check whether how long this will come. All those things you have to check. This is the cycle, thermal stability. So the thermal stability means you have to, whatever the PCM you have selected, that you have to check what is its thermal conductivity, what is its melting point, what is the thermal stability, all those things. For that, how to check all those things, some devices are there. So in the thermal conductivity means you have to check the thermal conductivity value of the things. That is in the thermal, that is called the thermal conductivity. And the thermal stability means you have to check through the that is called a thermal analyzer. So here thermal bath, they used to say thermal bath or thermostatic chamber bath. In that, the thermal cycle will be analyzed, how many number of cycles it will come, all those things. This will be, it will use the melting point and the later heat of the fission of the things, the thermal stability, what is melting point and later heat fission of the PCM, all those things will be there. That is, the device is called DSC, differential scanning calorimetry. So that if you place that PCM, it will give the melting point and later heat of fusion, how much amount of energy it will store, and what is its melting point, at what temperature it will melt, all those things it will give. So this characterization is very, very important before putting in an application. If you want to put new PCM in your power electronic system application, you have to think about these things. DSC means that is the differential scanning calorimetry. It will give the melting point, melting temperature, and then latent heat value, all those things. So this is about how that DSC will be. This is the device, DSC. How it is characterization. We have to. This is all same principle only. That is, reference material will be there. All those things. Anyhow, that is not related to your things. If you give the sample, lot of testing centers are there. They will give the values actually. And in our institute also, this type of equipment is also available. You can also use it actually. So based on that, you can predict the melting point. Suppose this is the, like that graph will come. From that graph, you can analyze that. So in this graph, it is 52.91. So that is melting point starts at 50. Phase change occurs at 52.91. That is around 53 degree. The phase change occurs, and then it will be completing at 60 degree. So after that, it will be completely phase change. Phase change take place. So this is the information you will get from the device. Similarly, thermal conductivity K value is also very, very important, that you have to measure it before putting in the application. So this here hard disk institute apparatus is there that will measure the thermal conductivity of the selected PCM. So in this device, it will give the that is thermal conductivity based on the that is, you can see the Q is equal to Ka delta T by L. This is a Fourier law of heat conduction. In the, based on the Fourier law of heat conduction, that is transient plane method. This device is called. This is some lot of devices are there. One of the device only I am shown here. Based on this principle, Fourier law of heat conduction, it will measure the K value. So now you can also find the K value for the. This is the experimental setups. K value for this properties you can find for solids, liquid, powder, any material you can find. For your application PCM phase materials, you can also find the solid state, what is the K value, and liquid state, what is the K value, all those things. That is the thing. So it depends on the temperature range will be there, what temperature you want. That is the thing, sir. So that you can place, this is the material you will be placed in the things. And finally, we are going to see about the, hello? Hello, is it audible? Is any problem? Hello? 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 So next is the thermal management in high power applications. Thermal management means, we will see, let us see what are the applications are there. You can see here. Through heat sinks. Suppose here I shown some of the. Hello?
Sir, please
Hello?
you continue, sir. I will mute them.
Okay, sir. Thank you, sir. Thank you. So this is here you can see the heat sinks. Some of the heat sinks are there where you will place the heat sinks at the backside of the power electronic components. You will place the heat sinks. So here heat sink study you can attach you can see number of fins for this small area. You have to calculate how much amount of heat is available. Accordingly, you can plan how many number of fins you can use. What is the spacing of the fins? All those things you can design it actually. This is the heat sink studies. And other thing is these are some of the forced air cooling method and jet impingement cooling and immersed spray cooling. All the things are other cooling techniques are there. You can see here. These are some of the application. So forced air means by means of fan you can use it so that it will remove the heat effectively. That's why in the CPU backside fan will be there. And then immersion spray cooling means whatever the target area is there, high heat flux area, in that by through nozzles it will impinge. It will be liquid pipes will be there, so that it will be through nozzle it will come, and then it will cool the entire surfaces, so that you should not spoil the surface like that. Immersive spray cooling will be there, and then jet impingement cooling. Jet impingement, these are the other cooling technologies are there. That is through nozzle, and then it will be selected only on the surfaces, film, like a film manner it will go. Here it's not completely submerged, it is immersed. Here it is a jet impingement cooler will be there, like a film kind of heat transfer will be there, so that it will effectively transfer the heat. And here you can see the heat pipe structures and immersion cooling of PCB and thermoelectric cooling concept and micro channel cooler, all those things. In the micro channel cooler means, so small micro channels will be there. That will be through that micro channel, you will send the fluid to pass through it, so that effectively heat transfer will be there. And immersion cooling of PCB. So PCBs are there. It will be immersed. It will be immersed in the so the proper cooling will be there. Immersion cooling of PCB, so that air or other liquid will be flowed. Other things, air will be flown. Circulated throughout the things, so that effective heat transfer will be there. And heat pipe structure. Heat pipe structure means wherever the heat in is there means there it will become vapor. You can see here, once the flow area will be there means it will become transfer the heat, and then when it comes to other places it will deliver the heat. Again it will be circulated back. So that's a heat pipe. Same fluid will be at one place, it will capture the heat, and other place it will be release the heat. That's the heat pipe structure. And thermoelectric cooling means, so here power source is required, you have to operate this. Whenever the power is given, so at one junction it will be hot junction will be produced, and other junction cold junction will be produced. So in the cold junction we are keeping near to the substrate, whatever the device is there, so that it will cool the surfaces. That is thermoelectric cooling. These are the things are there. And the other thing is through heat sink studies and CFD studies. Say we have to, I already told you, CFD, computational fluid dynamic studies, we can do that. In that we can heat flow, how much heat will be there, how much temperature, rise in temperature will be, all those things we can study through heat sinks, and then CFD studies will be there. All the things. This is about the different configurations of the heat sinks, whether circular, triangular, or rectangular, or pyramidal, or tree-shaped structure, or fins, plate fins, honeycomb structure. All those things you can study. You can study, and then you can, which one is effective, that you can study that. That is the thing. So all these things are related to that. That is thermal management in the high power application. Here also you can show in the high power application some of the things. That is concentrated solar power. The high heat will be there, and building components. I will just go very fast. This is for, we are using the PCM in the phase change material for the solar applications. This is the thing, and this is for the one place different PCMs we are using. PCM1, PCM2, PCM3 at different level it will transfer the heat. It will be, and in PCMs we are mixing with some alloys, metal alloy, to enhance the thermal conductivity, and then we are putting in the application. Similarly, you can also think about that. This is thermal performance enhancement of the PCMs. Some copper porous foam, nickel porous foam, metal, all the things. You can think about that based on your applications. And this is, we are using PCMs, not acid PCM. We are using a PCM balls. So the PCM balls also sometimes we are using, so that it will be, whenever heat is there, it will melt in the same chamber itself, and then it will be, whenever cooling is there, it will become solid like that. Heat balls, that is PCM balls are also there, shell and tube. And this is our application we are using, that is solar devices. This is for the solar devices we are using the phase change material, because here the temperature will be around 800 around 500 to 800 degree. There we are using the phase change materials, that is salt, organic salt we are using. Like that we are using that. This is for the thermal energy storage for the using solar, and then for power generation. Anyhow, this is different concept, but here the PCMs, thermal energy storage we are using organic PCMs or inorganic PCMs or utility PCM, we can use it. Synthetic oil, this is direct, we can cool it and then we can use it for our applications. These are the areas where we are exploring the PCMs, these things. And then in building thermal comfort, also we are using some of the PCMs for our building, so that the building heat will be heat transfer will be reduced. Anything. So up to this, these are the applications of the PCM. I hope now you got some ideas about the how to eliminate the heat in the high power applications. Now let us see what are the research activities we are doing at NIT Puducherry. We are doing mainly with the solar thermal, solar parabolic dish, trough, dryer, and solar cell. Anyhow, I will go very fast. And integration of PCM in solar thermal system. We are using means we are working in solar energy. Night time solar energy will not be there. So what will happen in the phase change materials we are using phase change materials, so that during the during the daytime it will absorb the heat, and then night time it will transfer the heat. This is the thing. That is night time will transfer it, so that the night time, even the solar energy is not there, it will continue its functioning. Actually, that is the thing. Then integration of high temperature solar thermal CPV, concentrating photovoltaic. That is the thing that also we are working, and heat transfer and fluid flow. These are our main research areas. I'll go very fast. I'll show some of the pictures so that you will come to know what are the research areas we are doing. We are working at the solar parabolic. This is a solar parabolic dish. I hope dish, you know, satellite dish and all. The same thing only. Here for power generation we are using. For thermal power, we are producing the steam, water to steam for our application. Sometimes we are using the nanofluid active cooling we are using, because we are using CPV. CPV means concentrating photovoltaic. You know, concentrating photovoltaic, you know, concentrating means high temperature. Whenever it is focusing, that high temperature will be there, we have to cool the solar cells. Otherwise, the cell performance will be deteriorate. It will not produce the expected VOC and ISC. That is the thing. So for that purpose, we are using the nanofluid cooling. That is the thing. So for that different concept here, low temperature desalination. Apart from that, we are working in the converting the sea water to drinking water. In the solar desalination we are working. And then this is the solar parabolic dish. In that we are using the CPV. CPV, that means concentrated photovoltaic, to cool the cells. This is the thing. So this is the one solar parabolic dish for converting for the steam we have placed the photovoltaic cell, that constantly photovoltaic cell, and then thermoelectric generator other side we are used to enhance the efficiency of the system. That is the thing. This is the way how to construct the dish and all. It is there. I'll go fast. This is the receiver. That receiver, we are working with the receiver. In the top side, we are using the thermoelectric generator, and bottom side we are using the concentrated photovoltaic. This we got patent actually. It gives almost 400 degrees centigrade. At 400 degree, it will effectively remove the heat also. That is the thing. This is the system we are integrated with this. This is, you can see here, thermoelectric generator we are not cooling. Thermoelectric generator we are using, and then bottom side we are used the concentrated photovoltaic. That's the things. And apart from that, different types of receiver also we are working. Different receiver and different tracking devices. Solar tracker, because sun is morning east to west it's moving, so that we have to track the sun. For that, photodiodes we are used, and then to track the systems, and we are used some tracking arrangement we are used. And then we are converting some filtering agent, that is con stem we are used for the filtrations to convert the sea water to drinking water. In this aspect, we are working with that. CPV modeling also we are working. How many number of bus bars, all those things, how many number of fingers should be there. Accordingly, the CPV parameters will be changed. And then CPV modeling we are using. These are the record CPV. And then the CPV will be integrated in the solar parabolic dish. We are converting 2D. That means 2D means one first D for DC power and second D for desalination. That is the thing. 2D, DC and desalination. So we want to convert that is CPV that is solar to electrical energy. At the same time, heat also we want to produce. That heat will be used for converting the seawater to drinking water. That is the thing. That is the concept. And the desalination, single slope, small setup is there to convert. Here we are incorporated the PCM, phase change materials, and night time also it will convert the seawater to drinking water. Because in morning time it will absorb the energy, night time it will utilize energy. That is the thing. So this is for the phase change material setup, solar dryer, solar desalination. Lot of set of experimental results are there to improve the, after using the PCMs, lot of enhancement of solar cell efficiency will be there. So accordingly, if you use PCM without any external agency, you can use the PCM so that your efficiency will be more. Here the concept is evaporation condensation rate. So that we enhanced a lot of things, lot of works we have done. Pins we have used, circular pins, we have hollow pins, solid pins we have used. In that hollow pins we have placed the PCMs, hollow pins, so that it further enhance the efficiency of the system. Like that we have done a lot of works, and we got our papers are also published, and then we got the patent also. And here we used to enhance the evaporation, some ridge guard, that is in Tamil it's called Pirkangai. That also we have used here in that to enhance the evaporation rate. And then to increase the efficiency, optimize the number of ridge guard we have used here. That also we published in there. And then the fibers material we have used to enhance the evaporation rate. We got patent also in this. Lot of things found the fibers we have used. And to enhance the evaporation, condensation, cooling also required. Cooling means condensation means cooling. For that, how to improve the cooling? For that, we have used some water also. Drinking channel water we have used, and then we have done a lot of work in that. That is banana fibers, jute fibers we have used. And then almost the glass cooling with the PV panel is there, like a glass transparent glass. In that small drip kind of water we have used. In that fiber we attach, and then it enhancement will be almost more than 100% enhancement will be there. So these are the things combined evaporation condensation things we have used. And then so based on the combined hollow fins, whatever the thing individually we did, now we have combined the evaporation condensation, hollow fins, pond fiber and sisal fiber we have used, so that the enhancement will be very doubled actually. 126% enhancement in the efficiency we got. Efficiency means whatever the, suppose the output is water, that water quantity is 100% more. Suppose 3 liter only producing means 6 liter we got actually, like that. So dryer means how to dry the things, how to remove the moisture content. For that we have the solar dryer we are using. And then drying kinetics we are studying how it is there. Different red banana, tomato, drying kinetics we are studying. And then fish, vegetables, all those things, drying kinetics we are studied. And the grapes, converting the green grapes to dry grapes, that also we are did. And then that kinetics we studied, how long it will take place, all those things, natural convection, forced convection, all those things. These are all our experiment set of facilities are available at NED Puducherry solar facility. We have donated the one solar dryer to the fisherman community. This is one of the big task we have given, solar dryer to fisherman community, so that they will normally dry the fish on the roadside. We ask them to dry on this device, solar dryer, so that 3 hours, instead of 3 hours to 6 hours, 6 to 12 hours it will take me. It will dry at 3 to 4 hours in this. And biochar with the PCMs to enhance the thermal conductivity. We are working with the biochars and the PCMs also we are working. These are some of the things. In the building components also we are working. Some of the PCMs to cool the building components. These are the equipment and testing facilities are available. Thermal conductivity measurements we have, and then we have the thermal conductivity measurements, and then we have the solar energy measurements, we have all the things. We have different setups, solar simulator we have, pyrometer, pyrolimeter, all those things we have. And these are the projects we got related to the solar, and then heat generation, CPV, concentrating photovoltaic module. And then the fuel cell also we are working. Part of that we have collaborated with NED Tiruchi, that is PH Tech Coimbatore. In that we have collaborated the DST UKRE projects. And then the BRICS NED Tiruchi also we have collaborated with life cycle assessment of CO2 reduction by carbon, by energy efficient hybrid biomass pyrolysis and gasification. And then we have got the recently project in core research in the solar parabolic dish concentrator with variable focal length using TEG and thermal region in seawater. And then we got also project along collaborated with IIT Madras and IIT Delhi with the desalination in Andaman. These are the projects. These are the patents we have that. So this is my Google Scholar citations. This is my Google Scholar citations. So there are always better ways of doing the things. Our challenge will remain to find them out. So here, whatever I said, the PCM, that is for our application, we said. So whatever the PCM you can choose for your electronics cooling application, choose it, and then you can do the investigate it. That's the thing. These are the references I used. Thank you so much. If you have any questions, feel free to ask me. I will answer to your queries.
So, dear participants, if you have any queries, please put it in the chat box, or you can ask directly to the speaker. Sir, I think there is no queries for you as
Yes,
of
sir.
now.
Yes, sir.
So thank you for your session, for your wonderful session. It was very
Yes, sir. Thank you,
informative
sir.
and very helpful for us. Thank you,
Yes,
sir.
sir. Thank you. Thank you. Yes, sir. Thank you so much, sir. Thank you, sir.
Thank you so much, sir.
Yes, sir. Thank you, sir.
But if you haven't filled the feedback, please do it. Thank you.
Thank you,
Thanks
sir.
for joining.
So I will sign out, sir. I will sign out.
Yes, sir. Thank you, sir.
Yes, sir. Thank you so much, sir. Thank you.
Thank you so much.